Okay, so look at page 20 for current of electricity chapter. Okay, this one, look at page 20 first, all right? Okay, wait on, let me just write this, page 20. Okay, now in an electrolyte, electric current is carried by charged particles or ions in the solution. What is not a possible value for the charge of an ion in the solution? Okay, keyword here, what is not possible? Okay, so this one is related to quantization of charge, which I mentioned first thing in the start of the chapter. All right, it was mentioned that all charges must be whole number multiples of an elementary charge. The elementary charge is 1.6 times 10 power minus 19 coulomb. Okay, so any charge that exists in nature, or rather in a stable configuration, there must be whole number multiples of E. So from here, what you want to do is that for each of these subsequent values, you try to find them in multiples of E. So what you do is this one, you will need to divide by 1.6 times 10 power minus 19. Okay, so in my case here, this one will be, if E is 1.6 times 10 power minus 19 coulomb, you find them in multiples of E. Okay, so this one is 4.8. Let me write this out properly for you. This one is 4.8 times 10 power minus 19 divided by 1.6 times 10 power minus 19. This one will be 4.8 divided by 1.6. You're going to get it as 3E. And then this one 1.6 times 10 power minus 19 divided by 1.6 times 10 power minus 19. You're going to get it as E. Then 3.2 times 10 power minus 19 divided by 1.6 times 10 power minus 19. This one is 2E. Last one, 4 times 10 power minus 19 divided by 1.6 times 10 power minus 19. You're eventually going to get the answer as 2.5E. Okay. So quantization of charge must be whole number of charges must be whole number multiples of E. Okay, so this one is whole number multiple of E, these first three, but the last one is not, it is 2.5, so this is not a possible value. Answer for this is actually D. Okay, so this one is for quantization of charge. Then after that, there are some things that I can also do from here. Okay, so I'm just going to be jumping around. All right, so just bear with me. Okay, the next one that we can do is probably page 8. No need now. Can I just jump straight to drift velocity? That is the easiest one for you guys. 56, is it? Wait on. 59. Okay, maybe I don't do this one first. Okay, page 22. All right. Okay, so have a look at page 22. All right, so I'm just jumping around. The easy ones, I'll probably just skip it. All right. Okay, have a look at page 22, June 16, P21. All right, so June 16, P21. Define the coulomb. Coulomb is unit of charge, right? Okay, so coulomb is unit of charge. Okay, right? So when you're asked to define, say, unit, definition of units must be in terms of units. Okay, in terms of units. All right. If they are asking you for definition of physical quantity, definition of physical quantity must be in terms of physical quantity. Okay, so under the first chapter, you learn what is the difference between physical quantity and units, right? So if, say, when you look at your definition questions, you have definitions of unit, please make sure that your definition is in terms of units. All right, your answer is in terms of units. But conversely, if it's definition of physical quantity, make sure your definition, the answer is in terms of physical quantity. Okay, so here, if they ask you to define the Coulomb, we know it's unit of charge. The equation for that has charge inside, the easiest one is I equals to Q over T, such that Q is IT. So in your case here, you will just say Coulomb is ampere second. All right. You won't say Coulomb is the product of current and time. If you say Coulomb is the product of current and time, your answer is in terms of physical quantity. That one is wrong. Okay. Please make sure that your answer is in terms of unit, since it's definition for unit. Okay, so I think I wrote it here already. You say it's product of current or time is wrong because it's in terms of physical quantity. If you say that Coulomb is unit of charge, this one, yes, is the obvious answer, so this one is also wrong. Okay, so write this one. All right, then look at part B. Resistor X is connected to a cell as shown in figure 6.1. All right, so all right, the resistor is a wire of cross-sectional area A and length L. The current in the wire is I. Show that the average drift speed V of the charge carriers X is given by the equation V is equals to I over NAE, where E is the charge on the charge carrier, N is the number of charge carriers per unit volume. Okay, so this one is the definition of, this one here is actually a derivation question. They are actually asking you to derive I equals to A and QV from the notes. Okay, so this one is actually asking you to derive that. And I also mentioned that please be careful about what N is. Sometimes N can be number of charge particles. Sometimes N can be number of charge particles per unit volume. Okay, so the same N can mean different things depending on the question. So your N here is actually number density, number of charge carriers per unit volume. So right now, derive it. Okay, so the definition usually is something like this. You can actually use that the definition, you can actually use that the derivation inside the notes if you wanted to. If I tell this one, the ones inside the notes, maybe that one is easier for you to understand. You can say that I is total charge over time. Total charge in turn is equivalent to N times V times E over T. Okay, sorry, N times volume times E divided by T. Then volume can be rewritten as AL NAL times E divided by T. Then this one, I can redo this as NAL over T L over T times E. So eventually you get NAVE. Right, so from here, therefore, V is I over NAE. This one is shown. Okay, so the simplest one usually when you want to derive the drift velocity equation is always this one. I is total charge divided by time. So total charge would actually be equal to the number of charge times E. So your number of charge here is this one. This one is number of charge, which is NV. Okay, because N is number of charge carriers per unit volume. If you multiply with V, you're going to get the number of charge carriers. Okay, number of charge carriers. So you multiply with E, you're going to get total charge. And then since V is total, V is volume, if let's just say this is the conductor right now, where you have cross-sectional area A, and then you have say length L, volume is actually AL. Okay, that's why you get this. Then from there, you want to group L and T together, L over T. This one will be equal to drift velocity. All right, so there are a number of steps involved. Okay, the one I've just written in pencil may not be that nice to read. If you want to, you can just follow what I just wrote. Okay. Okay, so that one is the derivation part. Okay, now, do you guys have the second part? Yeah, okay, you guys have the second part. All right, so now you have a 12 volts battery with negligible internal resistance that is connected to two resistors Y and Z as shown. Okay, you have two resistors connected like this. The resistors are made from wires of the same material. The wire Y has diameter D and length L. The wire Z has diameter 2D and length 2L. Find out the ratio of the average drift speed of the charge carriers in Y and Z. Okay, this one has to do with your ratio method. Okay, so if I try and look at this one for you here, say for example, let me just redraw the diagram here so that it's easier for you to see. You have a battery, you have your resistor. This one is Y, and this one is Z. Okay, so the thing here is that current will flow through resistor Y and resistor Z. Okay, now for both of these resistors, the equation I is equals to A N Q V applies. Okay, now maybe I change it to follow your question. ANVE. All right, I change it to follow your question. ANVE applies for both of these sections. Now you want to compare between these two, you have to use ratio, okay, because the question here is really asking you to find the ratio. So there are certain things that you can actually determine to be constant. Now, the first thing that you can see here is because the first thing you can say is the current is constant. Okay, this one is connected in series. There's no junction for current to split. Therefore, I is constant. This is number one. And then the second thing here, you see, they say that it's made of the same material. Now, under the lesson recording, I mentioned that resistivity is the property of a material. It depends on your material. If your material is different, your resistivity would change. Okay. Sorry. Okay, that one was resistivity. Another thing I was talking about different quantity. Material affects resistivity and number density. That was what I wanted to say. I was talking about resistivity to you. Okay, same thing too. The number density depends on the material that you use. Okay, so if you change the material, your number density would change. But if you're using the same material, your number density would remain the same. So here, since you're having same material, okay, same material, same number density. Okay, that one is correct. Then after that, you're talking about electron flow, right? Flow of electron. Electron always has same charge of negative E. Therefore, E is constant. Okay, because when you're talking about current flow is electron flow, right? So the charge of electron is always constant. So you can then say that in your case, I, N, and E constant. Therefore, V is inversely proportional to area. Okay lah, there's something here that I needed to do from here. Wait lah. Because here you have mentioned of diameter, right? Not area, so you have to change it to be in the form of diameter too. So pi area is pi over 4d squared NVE. Okay. You cannot use area directly here because the dimensions here is not area. They give you d. You have to change it so that it's in terms of d. So area, cross-sectional area is pi over 4d squared. Okay. So from here, I, N, and E constant, that would mean that V is inversely proportional to D squared. Okay, that's how you got this. Then from there, you can start to make the relation of Vy to Vz is actually dz squared over dy squared because it came from this. You're talking about Vy over Vz is 1 over dy squared 1 over dz squared. So eventually giving you this. So from there, you just sum in your values. Dz is 2d. Remember to square the entire term. Y has just d itself only. Okay, you just need to square the d. But dz, you need to square not just the d, you also need to square the 2. So eventually your ratio is 4. Okay. So this one is the ratio of their drift velocities. Okay, then the next thing here is show that the resistance of y to z is equal to 2. All right. Now, when you want to show that the resistance of y to z is equal to 2, there's an equation that you can use that relates resistivity, length, and d together. Now, when do you know you need to use the equation rho equals to... Generally, how do you know when you need to use this equation? R is equals to rho L over A. In general, when you're looking at your question and then you see that there's mention of resistivity and then there's mention of length and cross-sectional area, you know for sure most of the time you're going to use this. Okay, this is how you know whether you're going to eat this or not. If you see mention of length, you see mention of diameter or area, most of the time you will need to use this equation. You won't use this. Okay, this one, I know you also use this sometimes, but don't use this. Use this one right now. Okay, because you have mention of length, you have mention of material, you have mention of diameter. So here you can use R is equals to rho L over A, rho L over pi over 4d squared. Change area to pi over 4d squared. So one thing here that remains the same for both Y and Z is that they were made of the same material. So resistivity is constant. Okay. So this one, just like I mentioned, same material affects P and N, rho and N, same material, same N and rho. Okay. So if rho is constant here, that means R is proportional to L over D squared. This is the relation that you have. Okay. Then from there, you can work out the relation Ry to Rz is Ly to Lz times dz square over dy square. So how do you get this? This one I think is just simple maths. You can just easily do it out if you remember your maths. Ry to Rz is equals to Ly over dy square over Lz over dz square. Giving you this one. All right. So from there, it's just a simple method of doing the substitution. The question already mentioned that Ly is just L. Lz is 2L. And then dz is actually 2d squared. Okay, this one actually came from 2d squared. All right. Then dy was just d. You square it. Eventually, you get the answer as 2. Okay. So this is one way of doing this using ratio. Okay, so this one is okay. Then after that, I believe there was another part to this. Okay, determine the potential difference across Y. So I'm just going to clear off everything here. Find out the potential difference across Y. Okay, wait now. Determine the potential difference across resistor Y. Okay. Now you want to find out the potential difference across Y. Oh, this one has something to do with your potential divider equation, which you will learn under DC circuits now. All right. But this one, I believe at this stage in your study, you would have gone through DC circuit already. You have learned a bit about potential divider. Okay. Find out the PD across Y. They want this PD. Okay. Now, in general, you will eventually learn that if let's just say if I have a resistor like this, R1 and R2, and then I want to find out what is V1, or I want to find out what is V2, there is something called a potential divider equation, which tells me that V1 is actually R1 over R1 plus R2 times V in, or V2 is R2 over R1 plus R2 times V in. Say this one is V in now, all right? So there is a condition to use this equation. The condition is that same current must flow through the resistors. Okay. This one, if you look at the DC circuit lesson later on, you will notice that this one will be explained upon. But since you haven't gone through that, I'll just explain briefly to you first. Okay, you can use something called potential divider equation to find out PD across a series of resistors. But provided that you have the same current flowing through lah. Okay, this is the most important situation here. If you look back at this diagram here, just now early on, I mentioned that the same current flows through Y and Z. Okay, because this one is a series circuit. So I know I can use potential divider equation. So from here, I can actually say that the PD across Y would be Ry over Ry plus Rz times V in. Okay. Now, my V in is actually my EMF value of 12 volts. The question already told you what was the EMF. 12 volts here, right? This is your V in. Okay. But they never ever told you what was the value of the resistances in terms of ohm. But that is not an issue here because we can cancel it all. Now, if you look back at what you just found just now, value of the ratio of resistances of Y to Z is 2. So Ry to Rz is 2. I know that Ry must be twice the value of Rz. So when I want to use this potential divider equation, I put in the value of, I sub in just one of those values. Either I sub in for Ry or Rz, doesn't matter which one you sub, I sub in for Ry now. The resulting expression I get would be this one, 2Rz over 2Rz plus Rz times 12. So this one eventually becomes 2Rz over 3Rz Rz times 12. The Rz will cancel off. So eventually my answer is 8 volts. Okay. So this one, you not knowing what is the value of the resistance doesn't matter. You can use potential divider. Okay, so the answer is 8 volts here. All right. This one is something from your DC circuits, actually. But never mind, you will eventually go through that. Okay, so this one is all right. Okay, then next, find out the power dissipated in Y and Z. Yeah, this question has a lot of ratios inside. Right, so find out the power dissipated in Y and Z. All right, let's go through this one. Power dissipated in R and Z. Y and Z, sorry. Okay, power can be any number of things that you guys would have learned towards the end of the chapter. Is either P equals to I squared R, P is equals to VI, or P is equals to V squared over R. All right. So you can choose either one of these, but there's one that is most suitable. I would actually try to choose this one, the first one. Now, the problem with trying to choose the other two, which is this one and this one, you have a problem in the sense that you do not know the V. Okay. It's not to say you cannot know the V, you do not know the V. You do know the V. Okay, I just show you all the three different methods, just to make sure you guys understand why certain things are like that. Okay, wait, let me just clear off everything here. If you want to find the ratio of the powers using any one of these three equations, this one is fine. This one you can do. It doesn't matter which one you use. It's just that some of them are easier than the other. Okay, so let's just go with this one. You will somehow go back a bit to your DC circuit chapter again. All right, now, if you recall just now, you found out the PD across Y, which is 8 volts. So this one I know is 8 volts. So the PD across that would eventually be equivalent to 4 volts. This one you will learn under DC circuits Kirchhoff's second law, which tells you that the sum of EMF is equals to the sum of PD. In my case, E is equals to Vy plus Vz. Okay, so if my E is 12, my Vy is 8, obviously Vz is going to be 4. Okay, you can go about it in this method. All right, so from there, if you want to use any one of these equations to find out the ratio of the powers, you can. But let me just go through the first one here, which is P equals to I squared R. For both resistors, P equals to I squared R applies, but I know that the current is the same. So P is just directly proportional to R. So ratio of Py to Pz would just be Ry to Rz, which is what you already found in the previous question. You already found out Ry to Rz, which is 2. This one is the most straightforward answer. This is the most straightforward way to find the answer. Okay, but let's just say it did not occur to you to use this equation. You could have also used the second one. Okay, let me just show you the second one. This one, the color is so needed. Okay, you can also use P equals to Vi. Okay, so if I use P equals to Vi, notice that if I use it for these two, current will still be the same. I is constant. So P is directly proportional to V. So Py to Pz is Vy over Vz. Okay, so Vy you already found is 8. You also found from here that Vz is 4. So you see 8 divided by 4 gives you 2. You're still getting the same answer. Okay, this is using P equals to Vi. Now, what if I try to use V squared over R? You will actually still get back that same answer, but this one is actually the most tedious one. It's pretty much a waste of time to do because more steps there, but I show you anyway. This one will be P equals to V squared over R. You could actually get this as Py over Pz equals to Vy over Vz square, and then Rz over Ry. Okay, this one is the most complicated one. So eventually you see here, Vy was 8, Vz was 4, you square it, and then the ratio of Rz to Ry, you know that just now Ry to Rz is 2, so Rz to Ry is going to be half. So this one, what you can do is that this one is half. So this one will be 4 times half equals to 2. So you see, it won't matter which one you use right now. Either you use this method, P equals to I square R, P is equals to Vi, or P is equals to V squared over R. You by right will still get back the same answer, provided you know the rules properly lah. But using P equals to I square R is by far the easiest, most straightforward way to do this. Okay, so this is for this question. Well, this question is worth 12 marks. Right, okay, so this one is one part. Then I go on to another one just to drive the point across. Okay, what other questions here that I can do is, just now I did 59, is it? Okay, now we go again to drift velocity. Have a look at page 59. Have a look at page 59. Okay, page 59. November 18th, P23. So let me just kind of do this for you. Okay, so page 59, define Coulomb. Coulomb is something that we just did. Coulomb is just ampere second. This one is talking about the definition for unit of charge. So if it's in unit, everything must be in unit. So this one I mentioned to you before, right? So this one no issue. Okay, then the next one is electric current is a flow of charge carriers. In the following list, underline possible charges for the charge carriers. So then I mentioned to you, this is under quantization of charge. Charge will always be in multiples of elementary charge. Okay. Whole number multiples now. Okay. So all you just need to do is find out in terms of E, what are the possible charges. Okay. So this one, if I'm not mistaken, this one will be 5E. If you divide by 1.6 times 10 power minus 19, this is actually equal to 5E. This one is actually equals to E. And then the rest of it, this one was, just now we did this. This one is actually 2.5E. And then this one, okay, this one is 1.6, but notice that this is 10 power minus 20. Okay, so just be careful not to get tricked by that. This one is actually 0.1E. So this one is out, this one is out. So only this one and this one. Okay. So this one is again quantization of charge. Okay, the one that we want to do is the one that is below here. That one is talking about graph drawing. Okay, the diameter of a wire ST varies linearly with distance along a wire as shown. Okay, you have a conductor whose diameter varies with distance. Okay, there is a current I in the wire at NS of the wire. The diameter is D and the average drift speed is Vs. Okay, so here they mentioned to you at this end, you have drift speed of Vs. At NT of the wire, your diameter is twice. So now, sketch a graph to show the variation of the average drift speed with position along the wire between S and T. Okay, so they want you to show the variation of the drift speed. It will look like this. Okay, but why is it like that in the first place? So you again will have to refer back to your drift speed equation, which you know as I is a NQV, I is pi over 4 d squared NQV here. Now, what are the things that are constant? Now you see current will just flow like this right through. There's no junction for it to split. Therefore, I can say I is the same. And because this is talking about same material, there's no change in material. It's basically the same piece, same material. Number density is the same. And because we're talking about the flow of electrons here, the charge of electron will always be the same. So I, N, Q, and V are the same throughout. So from here, you come to the conclusion that V is inversely proportional to D squared. All right. Now, if you just look at these two, at D, you have Vs. Now at 2D, what should be your V, your drift speed V? So you have to relate to this one. If D is increased by 2 times, that means my drift speed will reduce by 4 times. Why is it 4 times? Because you have a squared term here. By right, it should reduce by 2 if there's no square, but because it's squared now, it will reduce by 4 times instead. You square the 2 to get the 4. So at 2D, you're going to have a quarter of your original drift speed. So it's quarter Vs, giving you 0.25 Vs. That's why you get 2D 0.25 Vs. So you look at your graph, you should have these 2 points here. This one is at S, this one is at T. So at S, your drift speed is just Vs. But at T, your drift speed is at 0.25 Vs. Okay, right? And then another thing here is this. You know these 2 points already. Please do not draw a straight line like this. This one is not correct. Now I know it's going to be a curve because of this relation. V is inversely proportional to D. Remember last time if I told you Y is equals to, let me get this straight. If I tell you Y is over X, the graph that you should get for Y over X is like this. So even if you were to change it to Y over 1 over X squared, it by right should remain roughly the same. It will be a curve. It cannot be a straight line. So you look at this one, V is inversely proportional to D squared. It's definitely going to follow a curve. So that's why your shape is like this. Okay? So this is how you're going to do this interpretation. Right, this one is just the graph drawing part. Okay. All right, so that one is okay. Then maybe I jump again to something else. Okay. Okay, so the next one that I could probably jump to is probably page 13, is it? Okay, no, this one not good. Now let me just see some stuff. Okay, this one seems pretty hard. 75, sorry, 45. Let me just see. It's either 45 or either 47. Okay, maybe we do 45 or not. Okay, 75, 73. Wait, now just let me have a look at some of the questions. Okay. Okay, now we do page 49. This one again is just the simple principle first. Have a look at page 49. Okay. This one is November 2017 P23. November 2017 P23. November 2017 P23. Is the last question. Okay, now you have a filament lamp that is rated at 30 watts, 120 volts. The potential difference of 120 volts is applied across the lamp. For the filament wire on the lamp, calculate the current. Okay, so this one is just simple application of your formula. So they tell you have a filament lamp, you have a PD of 120 volts across the lamp. What is the current through the lamp? If you know that it is having a PD of 120 volts, sorry, 120 volts, and having a power of 30 watts. So this one you can just strictly speaking use P equals to VI, 30 equals to 120I equals to 0.25 ampere. Okay, so this one is okay. Now the next one, find out the number of electrons passing at a point in 3 hours. Okay, so be careful with this one. When they say number of electrons passing a point in 3 hours, they basically want n. All right. So this one you can do it from the definition of your current. I is rate of flow of charge. Q is total charge. So you can break it out to number of charged particle times the charge of one particle divided by T. So N is IT over Q. Just sub in your values. You get 0.25 times 3 times 60 times 60. Because this one is 3 hours, you need to change to seconds. So 3 hours times 60 minutes times 60 seconds. And then divide by the charge of an electron, you will get the answer as 1.69 times 10 power 22. Okay, right, so that one is one part. And you get the answer. Okay, then after that, show that the resistance of the filament lamp is 480 ohm. Okay, this one is where you start to use your V equals to IR, or rather R equals to VI directly, V over I directly. You know the potential difference is 120, you know the current is 0.25, you can find out the resistance as 480 ohm. Okay. So this one should be okay. This one is just simple calculation, no issues here. All right, this one, the next one. Your filament wire has an uncoiled length of 580 millimeter, and it's made of metal. The metal has this resistivity at the operating temperature of the lamp. Calculate the diameter of the wire. Okay, so see, when you have mention of resistivity here, straight away you know you need to use R equals to rho L over A. A lot of times you will need to change the A to pi over 4D square. Because here the question also already asks you to find the diameter, right? So area change to diameter. So here, resistance is 480. You found it already. Resistivity is 6.1 times 10 power 7. The length is 580 millimeter. Divide by pi over 4D square. Solve that, you will get 3.06 times 10 power minus 5 meter. Okay, right. Now for part D, they tell you that the potential difference across the lamp is now reduced. State and explain the effect, if any, on the resistance of the filament wire. So when you reduce the PD across when PD reduce, current reduce, so less heating of filament, temperature drops, therefore resistance drops. Okay, this one is related to this chapter, this part in your current electricity. It's towards the end part. Okay, you are required to know the IV graphs for 3 different types of components: metallic conductor, semiconductor diode, and filament lamp. Okay, so under the lesson that you have watched, the three different components here, when you're talking about ohmic conductor or metallic conductor at constant temperature, just know that the resistance will always be constant. Whereas when you're talking about semiconductor diode, its resistance will tend to drop as current increases. Whereas for filament lamp, its resistance will always tend to increase as current increase. Okay, so why does the resistance of a filament lamp increase? Is mainly because we tell you the filament will heat up. When it heats up, your temperature increase. Okay, when your temperature increase, your atoms will actually vibrate more. It's actually going to oppose the flow of your charges or flow of your electrons. So if it vibrates more, it's harder for your electrons to flow through. That's why we tell you that resistance will increase. Okay, so here, based on that reasoning, when we say your PD has reduced, your current actually would have reduced too. So there's less heating of your filament, your temperature will drop. It's easier for your electrons to flow through, therefore resistance drops. Okay, your atoms of your filament will vibrate less when temperature drops. So it doesn't give you as much resistance. Okay, so the thing you can just probably say is just this: temperature decrease, thus resistance decreases.